Okay, so now we want to show a different application of compactness. Again, compactness for sentential logic. And the name compactness, probably for some of you, ring the bell, no? Because you've seen the compactness theorem in calculus, in analysis, before. And this is the same name, but it looks super different, right? Because it's formulas, like well-formed something about satisfiability of well-formed formulas. Doesn't seem similar, but actually underneath, in the core, they are combinatorially the same theorem. So here is compactness for the standard statement for compactness for the interval 0, 1. You may have seen like different variations, but they are all equivalent. And it says the following: if you have a covering of 0, 1 by intervals with rational endpoints, so you have a whole collection of intervals with rational endpoints, and all of them together cover 0, 1, the real interval in the real 0, 1, then finitely many of these were enough already. So there exists a number n such that the union up to n was enough to cover it. So whenever you have a every covering has a finite subcovering. Standard formulation of this is whenever you have a covering by open sets, you have a finite subcovering, but remember every open set in the reals is essentially a union of intervals of this form with rational endpoints. So it's equivalent. The other version is equivalent to this one because you will have to just for each open set consider all the intervals that union to that open set and put them all together, and then finitely many of those intervals are enough to cover the whole thing. Okay, so now what we're gonna do is use compactness for sentential logic to show compactness of 0, 1 in the reals. So we're gonna do a proof by contrapositive. So suppose that for all n, the interval 0, 1 is not contained in the union of all these finitely many intervals only up to n. Okay? So that means whenever you take finitely many, you do not cover the whole thing. And what we want to show is that when you take them all, you still don't cover the whole thing. That all of them together now, for all the i's in the natural numbers, you also do not cover. Okay, so if at all the finite steps you're not covering the whole interval, even when you get to infinitely many steps, you still will not cover all the intervals. So that means we want to find a real x that belongs to the interval 0, 1, but which does not belong to the covering of all of these. That's what we want. That's how we're going to show that is not covered, right? So something that is in 0, 1 is not covered, okay? So how are you going to find these guys? We consider sentential variable symbols a sub r, and we're going to call it a prime sub r for r in the rationals. Well, only in the rationals between 0 and 1. We only care about the ones between 0 and 1, but we can put them all. It doesn't matter. Think of a sub r as saying that x is less than or equal r. X is the one we want to build. We want to build this real, and this is saying that it's below the rational number r, and a prime sub r saying that x is greater than or equal r. Okay, so we're going to include all these variable symbols, and this is the meaning that we're going to assign to them. Okay, so now we want to write down sentences that say that if x is an element of 0, 1, which is not included here, then we want to write sentences that essentially say that x is an element of 0, 1 that does not belong here. Okay, so let's write that down. We want to define a set of sentences gamma such that if V is a truth assignment that makes gamma true, the x corresponding to it should satisfy this. So how do we talk about the x corresponding to this? Let's say x is the maximum of all the r's that are supposed to be smaller than r. Supremum of all the r's such that a prime r is true. Right, remember that A prime dr is saying that x is above r. So take all the r's such that we are saying that x is above r, and take the supremum of that. Since we're in the real, there exists such a supremum. So if we let x to be that guy, then x is going to belong to the interval 0, 1, but it's not going to belong minus the union over all I in the natural numbers of the intervals Ri, Li. Okay, so that's what we want. We want to define this set gamma that if we have a truth assignment that satisfies it, and then we satisfy x using the truth assignment, then we're finding this point that we want that shows that this interval is not contained in the whole thing. And what we're going to use for that is that we know this is true if you look at the intervals up to a finite point. And compactness is going to allow us to show that gamma is satisfiable and therefore that it has a truth assignment. And then from the truth assignment, we define dx. So how is that we're going to define this truth assignment? Okay, so first we want to say that x belongs to 0, 1. So we want to say x is above 0. Remember that a prime is the one that says that you're greater than or equal to this number. And we want to say that x is below 1. We want these truth assignments to behave correctly. So essentially we want to say that for every r, rational r, either is you're less than or equal r or you're greater than or equal r. So that's what that has. And also if you're above somebody and then you have another number below it, then you have to be above that guy. Let's recall up here that AR says x is less than or equal r, and AR prime, A prime r says x greater than or equal to r. So if you're less than or equal r, then you have to be less than or equal s for r and s in Q with r less than s. Right? You must satisfy that. Whenever you have a rational r below a rational s, r and s, and you have that your x is below r, then x has to be below s also. And the same on the other way around. If you have the same situation but now above, right? So in this case we still have r below s, but now we have x is above s, and if it's above s, then it has to be above r. Okay, so satisfying these things is going to allow us to show this. We have that x has to be above all the elements of a whole initial segment of elements, has to be below another set of elements. So we're defining a cut in between, and this is saying that well, yes, so there has to be no gaps between the ones that you're below 2 and the ones you're above 2. And but also we want to say that, what else do we want to say? We want to say that x is not in this union of these intervals, right? So how do you say that it doesn't belong to the interval Ri, Li? And we're going to say that x has to be less than or equal Ri and has to be greater than or equal Li for all I in the natural number. So this one up here, this one is the one that is saying that x does not belong to the interval Ri, Li. You're either below Ri or you're above Li. So either below or above, but not in between. That's what that one says. Okay, so now you have a way of assigning truths and false to each of these R's and A prime R's. Then that's going to give us an x, and the x is going to give us is going to be a member of the interval 0, 1, which doesn't belong to any of the intervals. So what we need to show now is that this is satisfiable. So we need to show that gamma is satisfiable, and again, the same as before, by compactness it's enough to show that every finite subset of gamma is satisfiable. So to show that, consider a set gamma 0, it's a finite subset of gamma, and we need to show that it's satisfiable. How are we going to do? Well, the point is that gamma 0 is a subset of gamma, so I may mention all these things. These are the things just for compatibility, which has to behave correctly. But out of these guys, it can only mention finitely many. Well, it mentions finitely many of all, but it's finite, so it only mentions finitely many of these. So how many? So it only uses finitely many of these i's. So let n be the greatest I such that the formula I, Ri, or A prime Li, so that's the formula we had right there, shows up in gamma 0. Gamma 0 is finite, so there is the largest one, right? So now to satisfy gamma 0, all we need to do is do a truth assignment that only considers those intervals, right? But we know by our assumption that for a finite set of these intervals, they do not cover the whole interval, right? That's our assumption by in our proof by compactness. In our proof by contrapositive. So no finite sets cover the whole thing, so there must be an x inside them. So take an x that belongs to 0, 1 and it doesn't belong to the union for I less than or equal n of the intervals Ri, Li. And now define a truth assignment. Let's call it W. And W, we're going to define it A of P is going to be true if and only if x is less than R, less than or equal R, and let W of A prime P be true if and only if x is greater than or equal P. Okay, and what do we have now? So this assignment satisfies, well, all these compatibility conditions, the first four lines there, because because they are just making sense of what these variables are, and it's going to define these ones up here, the last ones, because we are only considering the first n intervals, and x does not belong to those first n intervals. So it satisfies all of gamma 0. So gamma 0 is satisfiable. Okay? So gamma 0 is satisfiable, and this x might not work for, if you take a larger gamma 0, maybe you're going to cover x. So if you take a larger one, this x might not work, right? But for gamma 0 it works, and for every finite subset you can find a different x, which is going to give you a different truth assignment, which is going to show that this finite subset gamma 0 is satisfiable. And since every subset is satisfiable, every finite subset is satisfiable, we get that the whole thing is satisfiable. And then from the whole thing, we can define this x. Let's take in the supremum, because everything is compatible and the supremum is exactly the cut that we want. And since it's going to satisfy all these formulas up here, then we get that it doesn't belong to any of these intervals. Okay? So that's how you use compactness of a sentential logic to show compactness for 0, 1. See you guys in the next video.